Good morning, friends. In our previous session, we have talked about the grid integration of solar PV system. When I released the first video of standalone system of solar photovoltaic technology, in that case, I tried to explain the design of the solar PV system with an Excel sheet. Now in that case, the main application related lecture, that is this session, is typically how we can select the module and its connection. Means, suppose whether I need to install 1 kilowatt of rooftop power plant, then what should be the connection? Means, if one can connect two modules of 250 watt each in series and other modules of 250 watt each in series, and both the strings which comprising of two modules each in parallel, or either one can go with 4 series connected modules or 4 parallel connected modules. Usually this call can be taken depending upon the battery voltage, but if we can have the solar photovoltaic technology without incorporation of battery in general, then how one can select this solar photovoltaic modules? That is the main discussion of today's session. So if we can talk about the solar photovoltaic technology in its design calculation, in that case we are considering number of photovoltaic modules. In the background you may see a number of photovoltaic modules. This is the layout of the solar park, which might be a 1 megawatt, 2 megawatt or 5 megawatt capacity. So in the first glance we shall go with the design of solar PV system, its series and parallel combination, and then I'll try to discuss about the same for the standalone system. The lecture was already uploaded, how to design this standalone PV system. If we can talk about the silicon technology or wafer technology, it is a basic idea behind the solar cell. So currently we are going for the thin film solar or the multi-junction solar cells, and according to the type of material, that's what we have used, the efficiency is going to be changed, that is in percentage. In the case of multi-junction solar cell, the cost of the material is too high, but in front of that we'll get the handsome amount of good efficiency compared to what the other modules that has been used. Similarly, this is the solar cell parameters. That's what we are going to identify from the PV modules for various materials that is available for us. You will find this image everywhere in the internet and in different books. So let's begin with the concept. Our first problem is on calculate the new value of output current for the solar cells, which comprising of these 5 different cases of area, and we should solve this thing at the current density of the cell is 35 milliampere per centimeter square. So as we know that the current density is the ratio of the current upon area. In this case we are considering the short circuit current, but in this case the current density is given to us. As the current density is given to us and the area is given to us, suppose let's start with the 20. So in that case our area is 20 centimeter square. So our output current is this 35 milliampere per centimeter square into 20 centimeter square area. So my total output current for this centimeter square specific area of the cell is 700 milliampere. Similarly, one can do it for 30, 50, 80 and 100 centimeter square. So we are not computing this thing in detail in the PPT. So I tried to make a table of it. As it has been seen that the current density same, the cell area, the 5 possible cases that has been asked in the numerical, and the output current, that is ISC. So the output current is increased as the cell area has been increased, and similarly the ISC in ampere it has been found. This is what the concluding remark of this numerical. Now if you can check the same thing with the multimeter probe, as it has higher cell area from the digital ammeter, we can able to compute higher the short circuit current compared to the lesser area of the cell. It is almost double because we are considering the ideal cells for this discussion, means we are not considering any drop due to RSH and RSC. So how we can develop the procedure to estimate or design number of cells in the module. For example, a certain manufacturer used an advanced crystalline silicon cell wafer technology produces the solar cell with these parameters. Your VOC is 0.620 volt, VM is 0.510 volt at STC. The cell temperature reaches up to 60 degrees centigrade in operating conditions. So T is fixed in this case. So the modules are designed for the grid connection of PV plant. So if one can require to operate the voltage of the module is 13.5 volt, then we are going to estimate the number of cells connected in series for the preparation of this module, and the per degree centigrade rise in the temperature there will be decrement in the voltage of 0.0023 volt. Means if you increase the 1 degree Celsius for this material in this technology, then this much reduction in the voltage has been observed. So let us examine the number of cells as per procedure given above. So the following parameters are given: VOC is given, VM is given, cell temperature is given, and the percentage means decrement, that is 0.23% voltage that is going to be decreased. So for the first step we'll find out the VM. So the VM is given, that is 0.510 from the slide, from the previous slide. Now if VM, suppose if it is not given, then it is typically 80 to 85% of the VOC that is applicable for all the technologies. Our next segment is the find out loss of the voltage or a voltage loss of VM under the given operating condition. So comparatively 60 degrees centigrade is very high compared to STC. So the cell is operating at 35 degrees centigrade above the STC level. So the less in voltage there could be a due to 35 degrees centigrade rise is this 0.0023 into 35, that is 0.080 volt. So in that case, whenever we are considering at that time, we are having this much reduction in the voltage. So step 3, the available voltage at operating condition, that is equals to VM at STC divided by loss of the voltage, means minus loss of the voltage. So 0.510 is what the voltage is, and this much voltage has been decreased. So the available voltage at this operating condition is 0.430 volt. So if you can note the reading of the PV module, that is VM, that is given. So we are going to divide the required module voltage by available operating voltage to get the number of cells in series. It is very simple. The 13.5 volt divided by this much reduction. That's what we observed. So ultimately we'll get the 32 cells. In this case, only 32 cells must be connected in series to get the significant amount of voltage. Now sometimes when we need to get the higher output voltage from PV, higher than 15 volt or so, we will go with the certain aspect of the required voltage value. So in all the cases, this voltage will be a main quantity that is to be maintained. Say for example, a crystalline silicon PV module will have about 30 to 236 cells connected in series for 12 volt battery and about 60 to 72 cells for 24 volt battery. As I mentioned earlier, it is also depending upon the battery voltages. So in next segment we will go with the designing part again of the PV module for providing the voltage at maximum power point of Vm, that is 30 volt and 28.5 volt under operating condition that has been given 55 degree centigrade cell temperature. So using the cell with open circuit voltage of 0.62 volt and 0.002 volt decrement in Vm as per degree centigrade rise in the temperature. So we will go the same step. That's what we have done. So now we can find out the Vm, that is voltage at maximum point at STC for the solar cell. If Vm is not given, again we can estimate. So let's assume Vm, because over here the Vm is given but the VOC is not given. So in that case, if we can consider assuming Vm equals to 0.8 into VOC, then Vm of the cell is 0.8 into 0.62, that is 0.496 volt. Now in the case of the same, Vm is given 30 volt, that is Vm for the module is given, but we are considering Vm for cell, that is 0.496 volt. Now what we can do is we can find out the loss of the voltage, that is loss of Vm under operating condition. So the temperature corresponding to STC is 25. So in the previous numerical, the cell was operating at 60. Over here it is operating at 55. So 55 minus 25 is, again if you can consider, the 30 degree above STC. Sorry, over here it's a 30. So loss in the voltage per degree centigrade rise in the temperature is 0.002 volt. Therefore the loss for 35 degree is, in this case 30, because rise is over here now 30, 0.002 into 30, that is 0.06 volt. So this much reduction in the voltage in the cell that has been observed. Now we are having Vm, we will deduct it from the loss of the voltage, that is 0.49 volt. So now we are going to note down the required PV module voltage. So the PV module voltage is 28.5 volt, which is given. So now dividing the number of required modules from the voltage by available operating voltage to get the number of cells connected in series, the 28.5 volt divided by 0.49, that is the available voltage at operating condition from one cell. So this 0.06 volt has been reduced. So how much such type of cells are connected? So it is about 59 cells. Normally the PV modules are available of usually even number of cells. So I am considering the 60 cells connected in series, as shown in figure. So this is the higher open circuit voltage of the PV module as number of cells are connected in series. Now if you can go with the high power module, which comprising of higher area and the maximum power point, accordingly, and maximum power point for particular voltage and current point is given. With that, short circuit current and the open circuit voltage is also given. We need to find out the fill factor, maximum power point and efficiency of the cell. In this numerical, we need to consider the standard temperature conditions or standard test conditions. In this first session of the designing class, I should try to explain the same thing, all the aspect of the cell. In the upcoming session, I'll try to emphasize more about the module. But before beginning with this, what is the application of the cell on the module? As each of one knows that number of modules are connected in series for the preparation of single module, and how such modules could be look like. So these are the following parameters that has been given. The ISC is given 8.52 ampere, VOC is given 36.7. From this one can identify that this is a module, because if we can consider all the modules particularly in the array are connected in series and parallel combination, but for a particular single module, I repeat, for the particular single module all the cells are connected in series as per this diagram. So our short circuit current of the module and of the cell remains same, considering zero losses in this case. Otherwise that much I square R loss or the heat loss might be developed. Then we'll go with the next point, current at maximum power point, voltage at maximum power point, light input at STC 1000 watt per meter square, and the area which is given 1.62 meter square. So if you consider the maximum power point PM, it is a multiplication of IM into VM, that is 250.48 watt. Now the fill factor is the highest rectangle that could be dim fitted in the IV curve of the PV module. Mathematically, it's the ratio of maximum current into maximum voltage, means voltage at MPP at the particular radiation and the current at MPP for the particular radiation, and hence power at MPP for the particular radiation. Over here we are considering it STC. So PM, that we can take it from here, IS and VOC is given. So we get the 80% of the efficiency of the fill factor, means the fill factor is 80%. Talking about the efficiency of the module, the efficiency equals to obviously output upon input, but over here in input power is also depending upon this area. So if you can consider this P in, that is 1000, I'll multiply with the area 1.62, and the P max is given 250.48. I'll multiply with the 100, I'll get the 15.46%. Over here P in we are considering at this 1000 watt per meter square radiation. So watt per meter square into this meter square will get the watt. So this is the new thing to find out the efficiency of the PV module. So in next session I'll try to explain how we can connect certain modules with the series and parallel combination to achieve the multiple output in terms of series connected PV modules, the voltage will rise, and parallel connected PV modules, the current will rise, and the mixed combination of the same. For this time, thank you very much.